Welcome, beloved learners. Welcome to the channel. Welcome to Black Slides Online Secondary School YouTube channel. Remember, this is the place where you learn the sciences, namely physics, biology, chemistry, and mathematics. But if you want to enroll for more subjects, we also offer computer studies, agriculture, additional mathematics in our main Black Slides Online Secondary School platform. For you to be there, you shall simply contact us on the numbers that have been shared here, and we'll be able to give you the information that you need. Alright, so once again, welcome to this lesson. This is lesson number 2 of the topic called radioactivity. We started looking at radioactivity, I think, yesterday, where we looked at the definitions of the terms radioactivity and the radioactive decay. We also looked at the properties of the 3 types of radiations, namely alpha, beta, and the gamma radiations. So without further delay, welcome to today's lesson. We are going to be discussing more aspects of the topic radioactivity. Alright, so consider, like I said, subscribing to the channel so that every time we upload a new video, you become the first to know. You don't miss anything. Great. Alright, so welcome to subtopic radioactivity. The topic is radioactivity, subtopic radioactive decay. And we are going to be looking at nuclear equations. Alright, not chemical equations, but nuclear equations. Alright, so we said yesterday in lesson 1 that the unstable nuclei of elements can undergo a radioactive decay in which the nuclei disintegrate spontaneously and emit a radiation, which can be alpha, beta, or gamma radiation. And in the process of doing that, we said that a new element is formed. So the original element, which undergoes a radioactive decay, the original element or nuclide is called a parent. A parent, a baba, a bamboo, or mother. Alright, parent. And the resulting new element, which is formed as a result of the decay process, is called daughter element. A daughter, a girl, eh? Alright, daughter element. So the original element, which undergoes nuclear decay, radioactive decay, is called parent. Alright, and the new element thus formed is called daughter. So what happens during alpha decay? When an alpha particle is being released from the nucleus of a parent, there's a change in the nucleus. So if a nuclide X decays by emitting an alpha particle, its mass number decreases by 4 and its atomic number decreases by 2 to form another nuclide or element Y. I hope we are together there. All right. Supposing that we have an element which is undergoing an element X which is undergoing an alpha decay or releasing an alpha particle or emitting an alpha particle. Remember that X stands for any element whose nucleus is not stable, and it is to undergo radioactive decay. And the A is mass, mass number, while Z is its atomic number. Atomic number. All right, so in the course of undergoing radioactive decay, the mass is going to decrease by 4. Why? Because an alpha has a mass of 4 and the atomic number of 2. So when this is being emitted from an element X, it means the mass number is going to go down by 4. It's like we are subtracting the mass, 4 from the original mass. All right? So an alpha is being emitted. When an alpha is being emitted or released from the original element, which is the parent, its mass number is going to decrease by 4. So you have A minus 4, and its atomic number is going to decrease by 2. Z, which is atomic number, minus 2. And for this equation to be fully balanced, don't forget to add the alpha particle there. Remember that an alpha particle is identical to a helium nucleus. Yeah. Such that if you add the top numbers, the top values, in this case we have A minus 4, add this 4 here, you end up having A, which is the original mass there. All right? So this equation, therefore, in terms of change in mass, is concerned in terms of change in mass, the masses are balanced. So making sure that when you add this to the 4, you get the original mass there. Okay, so don't forget to add the alpha there in terms of helium nucleus. For example, suppose polonium is undergoing an alpha decay, is emitting alpha. All right, its mass is going to decrease by 4. So all you have to do is from 210 subtract 4, which will give you 206. So that 4 is going to appear on the helium nuclide there, such that when you add 206 plus 4, you should be able to get the original mass, which is this one here. All right. In the same way, the atomic number is also going to decrease by 2. So we have 84 subtract 2. You have 82 there. Don't forget to show this 2 which has been subtracted. Don't forget to show it on the helium nuclide there. So effectively, if you take the 82, add 2, you should be able to get the original atomic number, which was 84. 84. All right, so that's what we are saying for an alpha decay. However, if If an element decays by emitting a beta particle, the mass number remains constant, remains the same, but its atomic number increases by 1. All right, remember that a beta from our first lesson yesterday, lesson number 1, we said that a beta is simply an electron with a mass of 0 and a charge of -1. All right, so don't forget this, because it shall help you when you are working out the nuclear equations. So let's go back to our original element, which is X, which has mass of A and the atomic number of Z. So it's losing, we are subtracting a beta from it. So what's going to happen is, because a beta has no mass, that means the mass of the new element is going to be A minus 0, which is just A. But the atomic number of the new element is going to be Z plus 1. How? You take the original atomic number, which is Z, and then we are subtracting the charge on beta, which is -1. So -1, Z minus -1, a minus and a minus will give us Z plus 1. Therefore, the new charge, our atomic number, is going to be Z plus 1. Also, don't forget to add at the end, to add the beta particle with its mass and the charge shown. All right, so such that the equation becomes balanced. So if you take the A on the new element, the mass, add 0, it will give you back the original mass. Similarly, if you take V plus 1, which is the charge on the new element, the daughter element, plus the -1, it is going to give back the original atomic number, which is Z over here. All right, so that's what we have. I hope we are together. If this is the first time you have logged into this channel, consider subscribing to the channel so that you don't miss on anything that we upload in the future. All right, let's look at a specific example of a beta decay. Suppose an element such as beryllium emits a beta particle. All right, so like we said, we are taking away beta, this one, whose mass is 0. That means the new mass is going to be 11 minus 0. Therefore, the mass remains the same, but its atomic number is going to increase by 1, so it will be 5. So from 4, we subtract the charge on a beta particle, which is -1. Then we have 4, a minus and minus will give us a plus, which is 4 plus 1, and that's 5. That's this 5 here. All right, and also don't forget to add at the end, to add the nuclide or the symbol for a beta particle. Very, very important to note. All right. Unless you have questions, don't hesitate to leave your question in form of a comment in the comment section below, or simply contact me on the number that I shared to you earlier on. All right, let's look at what happens when a nuclide emits gamma radiation only. Remember that gamma is a pure radiation. It belongs to a band of other radiations which is called electromagnetic spectrum. It's pure radiation, it's not a particle. Therefore, when a substance or a particle an element is emitting gamma, its mass and atomic number will not be affected. So we are saying that emission of gamma rays has no effect on the mass number and atomic number of an element. Let's say, for example, we have a nuclide X with mass number of A and the atomic number of Z, which is emitting a gamma. Is emitting a gamma. Remember, gamma is like this. Alright, so we are removing gamma from it. Its mass is going to be the same. In other words, the element does not change its identity. We end up having the same element, and it's not affected. Alright, therefore, the equation is going to be as shown here. We are going to have the original element, then you add the gamma. Gamma is just some kind of y, and then you have 0, 0. Such that if you add the top numbers, you add a plus 0, you get back a, which is this one here. And it shows that mass is not affected when an element emits gamma. Similarly, its atomic number will also remain the same. Z add 0 is going to remain Z, as shown there. Alright, so that's what we have. Let's look at a specific example. Suppose we are looking at cobalt. Cobalt has a mass of 60 and the atomic number of 27. So it's emitting gamma. Alright, when it emits gamma, the element will remain unchanged. It's going to be cobalt with a mass of 60 and atomic number of 27. But don't forget to add the gamma symbol there. So gamma, which has no mass and has no charge, when you add the numbers up, you should be able to get back the original masses, mass and atomic number respectively. Alright, so that's what we have. Let's look at an example just to substantiate what we are talking about. Alright, suppose an element such as radium undergoes a radioactive decay by emitting half a particle to form a daughter element Q. As in the equation shown below, determine the values of X and Y. Alright, so we have X here and Y there. Mind you, this is a daughter element, and this is our parent. Radium is the parent. And we are told that it's emitting alpha particle. So, an alpha particle, remember, is just the He with a mass of 4 and the atomic number of 2. Alright, so in order to form the new element, it means the mass is going to decrease by 4, so subtract 4 from 226, and atomic number shall go down by 2. Therefore, it means X is going to be equal to what? X is going to be equal to 226 subtract 4, which means it's going to be 222. So X is 222. Similarly, the atomic number is going to go down by 2. So in this case, we shall have alright, Y, this Y here should be equal to the original atomic number, which was 88, subtract 2, which gives us 86. Alright, so which is this one here. So you can do that in any case where you're given enough information. You should be able to find what is not known. All right. All right. Now, I would like to leave you with this work for you to use the same techniques to solve these problems. All right. So you have number one is saying the following reaction is part of the radioactive series. Identify the radiation X and determine the values of B and C. Determine the values of B and C. All right. Determine the values of B and C. I'm sure B is this one over here. All right. Number two, the following is part of a radioactive decay series. A nuclide which is given by this information here decays to X by emitting an alpha particle. X decays to Y by emitting a beta particle, and Y decays to Z by emitting a beta particle. Alright, so what we are going to do is, what you are required to do is to determine or to write down the nuclear equation. So the nuclear equation, you can work it out and compare it with this one given here. Number three, you are told that uranium, this one here, decays to polonium, this one, by emitting alpha particles. Find the number of beta particles emitted and write down the nuclear equation expressing the decay process. All right, so I would like to leave you now. Please work on these questions and submit. I'll be glad to see your responses. All you have to do is write the exercise and take a picture of your work and send it to my number. Then I'll be able to give back feedback. All right, consider subscribing to the channel once again so that you don't miss on anything that we upload in future. My name once again is Mr. Paul Chilora. Bye-bye.